we were talking about the group, the infinity, and it's the group that can be described as the semi-direct product, or equivalently as a free product. So it can be described as a semi-direct product. Or it's the same as a free product of two groups. For x equals to a and y is ab. And we studied Banach representations and irreducible representations and the notion of spectrum for this group. So I would like to recall everything because it was quite complicated. First of all, irreducible representations. So irreducible representations has dimension at most 2. And the two-dimensional representations are in bijective correspondence between complex number without 1 and minus 1. So we have a map. We were denoting the set of irreducible two-dimensional representations by d infinity 2. And we have a map. So it's a set of isomorphism classes of two-dimensional irreducible representations. And we have a map from C without minus 1 and 1 to this set. And for a complex number C, we decompose it into such sum for some lambda. So there always exists such lambda, and it's the solution to the polynomial, to the quadratic equation. And the presentation for this C is denoted as lambda p, and A acts like this matrix in it, and B acts as the diagonal matrix. And so for lambda and lambda inverse, these representations are isomorphic, and they are irreducible as long as lambda or C, equivalent to C, is not 1 or minus 1. So we have a map, and actually this map is a bijection. So we just identify the set of irreducible two-dimensional representations with this complex manifold. And so we give this set a topology as in here. So the same topology. And also we have 4 characters for this group. So I've came up with a new notation for the characters, and it would be, so we have characters, and I call them he1, he2, and xi1, 1, Xi2. So, and on generators, we have Xi1 on A equals Xi, no, 1 and 2, but plus and minus, because 1 and 2 are confusing. He plus on A equals he equals 1. He minus on A equals minus 1. He plus on B is 1, and it actually equals he minus on B. And for Xi is the same on A. Xi plus on A is 1. Xi plus Xi minus on A is minus 1. And Xi plus on B is the same as Xi minus on B, and it's minus 1. So, and it's 2 pairs of characters, and we attach these characters to two-dimensional representations as double points to these holes. So as we can see here, we have eigenvalues of B equals lambda and lambda inversed. So when we approach to 1 or minus 1, we have eigenvalues of B equals 1 or minus 1, depending on the point. And eigenvalues of A are always 1 or minus 1, because it's involution. So it is actually natural to think that these pairs of characters are attached to points 1 and minus 1. So we have like this a complex plane, and a complex plane without points 1 and minus 1 minus 1 is the set of irreducible two-dimensional representations, and we attach here the pair of characters. So we attach here the pair of characters he plus minus B, because he plus minus, because he plus minus B equals 1. And here we attach the double point of the character Xi, And the topology is usual for double points. You might think of it as two complex planes glued together by the open subset without 2 points. So we have like a commutative diagram, C without 1 and minus 1 is a subset of C. This is a subset of C here, and we may form a sort of crossed, not cross product, but the opposite. I can't recall how to call it, but we here form the space of irreducible representations as a non-separated complex manifold. And so I think everyone understands what does the topology with double points mean.
Is this a push out in a suitable category?
Yeah, I think it's a push out if we in the category of non-separated manifolds. So if we allow, so it's usually a part of definition of a manifold to be Hausdorff, but we may equivalently drop this from definition and allow non-separated manifolds. And so it's like an atlas because we have both of these are affine sets, and they are affine open subsets of the infinity, but they are glued together in some wrong way, in some non-natural way. And so here are double points arises, where double points arise. And we want to define a spectrum of representations, and we actually did that. So I would also like to recall the definition. So if V is a Banach representation, of our group D infinity, then we can form, we can use that, let's make like this, V with P, homomorphism. We know that P of X and Py are involutions, and they are independent involutions. There are no additional requirements for this involutions. So we may decompose V into the eigenspaces of X. Even if it's Banach space for involutions, it always works. So every eigenvalue of an involution is every element of the spectrum of the involution is an eigenvalue. So we may decompose V into a product of V plus for X and V minus for X, where X acts like identity on V plus, and by multiplication on -1 on V minus. And in this decomposition, we have X acting like matrices, X and Y acting like matrices, and Y acting like also like a matrix. And those matrix elements of Y are tied together with the condition that Y is an involution. So I wrote down last time. I wrote down 4 equations for Y squared to be an identity, but we used these equations for an important result, and precisely Y plus plus and Y minus minus are operators on V plus and V minus respectively. So we can compute its spectrum, and actually turns out that we had a theorem that the spectrum of Y plus plus without 1 minus 1 equals to the spectrum, and 1 and minus 1 are not always in the spectrum, but I mean here that we drop them if they are in the spectrum, equals minus spectrum of Y minus minus without 1 minus 1. So we again receive this sort of asymmetry in points 1, -1. And this is not a coincidence. And actually, it's like a very important rule. We use it to introduce a spectrum. So definition of the spectrum as a spectrum of the joint spectrum or Taylor spectrum of representations is a subset of the infinity with hat. And what we have here, so we are defining them by defining the spectrum by parts. So the representation of the four lambda b, so two-dimensional representation is in spectrum of the infinity v, if and only if lambda plus lambda minus pair lambda inversed is in spectrum of y plus plus, and using the theorem, it is equivalent to lambda plus lambda minus 1 fractured by 2 is in minus of spectrum of y minus minus, because lambda we consider here lambda which is not 1 or minus 1. So by theorem, it's all the same. And for a character, characters, we have that he plus is in spectrum if and only if 1 is in spectrum of y plus plus, minus is in spectrum if and only if 1 is in minus spectrum of y minus minus, or minus 1 is in spectrum of minus minus. And for Xc, all the same, but with minus 1. So Xc minus is in spectrum if and only if minus 1 is in spectrum. And the same for Xc plus, but I won't write it. This is also and the signs are chosen in such way that the spectrum of irreducible representations, if X is irreducible, not depending of whether it is two-dimensional or one-dimensional, then we have a spectrum of X equals the class of X, or simply X, but it's better to write the class of isomorphism of X. Yeah, and here may be different situations actually. So it may as we will see, for this part of the spectrum, for two-dimensional parts of spectrum, everything is easy, and actually the commutative theory of holomorphic calculus extend here naturally to a non-commutative one. We just multiply ordinary holomorphic functions on some other operators and receive a bigger algebra of non-commutative holomorphic functions. But in the neighborhood of characters, everything is a bit more complicated, and we have to resolve everything by hand, but hopefully we have an important theorem, and I will state this theorem for the characters of the form he, and it is also true for the characters in the form xi. So suppose, let's first start with the definition, which will be helpful. So we call a subset of the infinity symmetric. We call the arbitrary subset, let's call it S, subset of the infinity with head symmetric. I know whether it is a really good term, but it will help to talk about it. If two conditions are satisfied, first of all, if he or I is in S, then he J is in S2 for I not equals to J. So if we have so I may be one or maybe okay, maybe plus or minus. Actually, here are four conditions. Here, two conditions. He plus, if he plus is an S, then he minus is an S, and if he minus is an S, then he plus is an S. And the second condition is the same for the character xi. So what I have just written is that the subset is symmetric if it, for every double point, it either contain both. It either has both or no one. So, and in some sense, we can treat such subsets as commutative spaces. And also, if the subset is not symmetric, this is asymmetric. And the case of symmetric spectrum is we're not interested right now in case of symmetric spectrum, but we would like to study the case where the spectrum is asymmetric. And there was a theorem. And the theorem says that that if, so I will state this theorem only for one pair of characters, but here everything is the same if we change this pair of characters to another. So actually there will be four cases, and I will write down only one case. So if he plus is in spectrum spectrum of V, and he minus is not in spectrum of V, and the theorem will also work if we replace he plus with he minus, for example, and he minus with he plus, or he plus with xi plus, and he minus with xi minus, and etc. But it will be messy if I will write everything. So I just formulate for this. Then there is a decomposition of V into V0 and V he plus, such that we have the following: that V he plus is a subspace of he plus semi-invariance. So the infinity acts on he plus by multiplication on this character, on he plus. And spectrum of V0 is does not have he plus or he minus. And it is important that spectrum of direct sum is the sum of spectrums. So so both he plus and he minus, both he plus and he minus are not in spectrum of V. So the spectrum of the direct sum is the union of spectrums. Yeah, and also the same theorem for another three possible pairs of characters. Yeah, we may change pluses and minuses, and we may change he with xi. And also this fact can be reformulated like this. So if spectrum of V is asymmetric, metric, then we have a decomposition. V equals to V, say 1 plus V0, such that spectrum of V0 is symmetric, and spectrum of V1 has say V1 is either a spectrum of V1 has only one or two characters. We can say like this, that it's in the subset of one-dimensional representations. And this fact is crucial for constructing a presheaf of functions, because we will do this. First, we will construct such a presheaf of functions for
So in the previous case, when in the case of double point, V0 was invariant subspace, is it? Or what was V0?
no, invariant.
Yeah, that V0.
Here is V0. V0 is a in some sense bigger part. So this is just the set of the subspace of semi-invariants. So the eigenvectors for the infinity with the character he, and V0 is the subspace with is the residual subspace.
So it's not invariant, right? It's just subspace.
What?
It's not invariant, right? With respect to D.
No, it's invariant. So
it's invariant. Okay.
Yeah. So it's they are both invariant. Yeah, it's decomposition as modulus, and it is invariant, and so it's a representation, and we can compute its spectrum, and the spectrum is does not contain both characters.
Okay, I got it. Thanks.
So this theorem, as a conclusion, as a corollary, has the fact that if the spectrum is asymmetric, so if it has only one character from the pair, has only one double point, then we can decompose V into some of subrepresentations such that V1 has V1 has now symmetric spectrum without those double points at all, and V0 has V0. Okay, let's write as in previous here. V0 and plus V1. V0 has is symmetric. V0 is symmetric, and V1 has only characters in the composition. Actually, V1 is either a character subrepresentation, so either D infinity acts on V1 as a character, or V1 decomposes into some of two such subrepresentations for two different characters, for C plus and he plus, for example, but not for the pair of characters from one double point. Yeah, and this is important for our non-commutative functional calculus, because it turns out that it is easier to construct the non-commutative holomorphic functions for symmetric open subsets, and then we can use this decomposition to extend this theory to non-symmetric open subsets, and it will be done in a very stupid way. We will just act on both summands independently. So we will act on V0 as by holomorphic functions, and we act on V1 on character subrepresentations of V1 just as like complex numbers. But
sorry, it's a sort of a localization theorem, right? You can always skip this double point, but it seems you can continue this decomposition, right? Always skipping this point, I mean double point. Am I right? Is it you can continue this decomposition, right?
Continue. So, for example, it can be the case. So, like V equals to V0 plus V, say, he plus V xc minus, for example, or he minus xc plus, and this is what I call V1, and it's the sum of just eigen subspaces. So our group acts here and here by multiplication on two characters.
Okay.
Yeah, and we use this fact for localization. So we are more interested in this part in the decomposition, and here we may act only by some multiplicative constants. So it's quite actually this fact makes our invention of non-commutative holomorphic functions not as interesting maybe as it might be, but although I think it is still worth studying. So so let us start with the symmetric subsets, and let us recall this matrix for y, and the matrix for y is y plus plus, y minus minus, y plus minus, minus plus, minus minus, and we assume now that the spectrums coincide. We assume that the spectrums coincide, no, with minus here, because it's like wasn't part of the theorem with minus. And here, so the spectrum of representation is symmetric. And so we want to think about what holomorphic functions we can construct. So if we know spectrum of y plus plus and y minus minus, we want to take holomorphic functions on y plus plus and y minus minus. So we may take like this function. Say we may write here f y plus plus, say f plus g minus at y plus plus y minus plus, and then we take g plus, say g plus, say y plus minus g plus and f minus on minus y minus minus. So we take minus here because to have the same for these functions to be determined on the same open subset. So and f plus, f minus, g plus, and g minus are holomorphic on some u, on some open u containing the spectrum of y plus plus. And we can take these functions. Obviously, we can also multiply y minus plus here, y minus plus, for example, to the right on some function, from here from y minus minus, but it turns out in this case that if we have G minus Y plus plus, Y minus plus, minus plus, it's essentially the same that Y minus plus multiplied by right on G minus for Y minus minus. It's a consequence of the relations on Y on Y's on matrix elements on Y of Y, and since the spectrums of Y plus plus and minus Y and Y minus minus are the same, we receive here that everything is correct. So here everything is actually correct and nice. This is what we may expect from the homomorphic functions on some symmetric subset. So we just use such matrices, but it's important to write down the multiplication of such matrices, but it's actually not very hard. So let me one moment. So it can be actually done, and I will now introduce some way how to write everything what was just said more formally. So the observation here is that we proceed to a group algebra. So we have a group algebra of D infinity, and the centrum of the group algebra is the polynomial algebra generated by the element Z, and Z equals B plus B minus 1, B minus 1, yeah, so yeah, this is the central element, and this central element generates the whole centrum, and the whole group algebra is a free module over its centrum. Module over its centrum, and the generators of this module are 1. So I have to moment. I use these generators 1 plus A, 1 minus A, fractured by 2, 1 plus A2, and then B. Yeah, so it's a free model with this basis. So it's a free model of rank 4. And what we want to do now is to make an algebra of holomorphic functions as a free module over holomorphic functions over holomorphic functions in Z. So, for example, we define the holomorphic, the entire functions, the set of entire functions, d infinity. So on the all of the d infinity, to be a free model, we define the entire functions to be a free module over the ordinary entire functions ordinary entire functions with them in the variable z. I don't know actually how to point it out. With as a free model of rank 4 with the same basis, and relations. So it's actually one actually should check that the multiplication is can be lifted to a multiplication on this free module. So the multiplication here can be lifted here. That is not very hard, but it's rather technical. You just have to write down all the relations between this in this basis, and to observe what is going on in there. And
but I'm sorry to interrupt. So my question is this the same as taking the tensor product of the group algebra by homomorphic functions over the polynomials? So kind of extending scalars, or this is something different maybe?
Yeah, I think it's the same actually.
Because if we interpret this in this way, then it will be clear that the resulting object will be, in fact, an algebra over the homomorphic functions and free module of the same rank.
Yeah. So yeah, you're right. So it's the same actually.
Mm-hmm.
So it's the infinity is tensor over z, but c in z over centrum with the entire functions in z. Yeah, that's right. I think that's what we need actually. And also it's
there's a space, that's true, but as an algebra it's infant, right?
What?
Maybe there's a space, that's true, the space identification, but is it true as an algebra? It's a bit...
Yeah, it's an algebra. So we define a multiplication.
So you're saying it's an algebraic isomorphism, is it?
Yeah.
Okay.
And also it's an Arens-Michael envelope, and you can read more about Arens-Michael envelope for this algebra in the work of Oleg Aristov. He pointed, he showed me it after the last seminar. So it's like a good candidate for entire functions, and so we do actually the same for an arbitrary open subset, but here we should identify symmetric subsets of the infinity, symmetric open subsets of the infinity with open subset of complex numbers, but that is actually easy because we have the infinity hat is C without 1 minus 1 with the set of characters. Yeah, and they are attached to 1 and minus 1. But symmetric sets may have double points only in pairs. So we have surjection on just C, and on this part it is trivial. So the representation of form lambda b goes to lambda plus lambda minus 1 fractured by 2. And for characters, he plus minus 1 goes to plus 1, and C, both double points go to minus 1. So just a surjection. One may think about it as map between spaces induced by algebra homomorphism. So also obviously in non-commutative geometry, even if there are some non-commutative spaces, there may not be such homomorphism, but for the case of centrum, it should always exist. So we have an inclusion of centrum to the group algebra, and the map which we constructed now is like a induced map on spectrums. And the latter is commutative space and the first is not commutative. And it works just fine. So what we do here, here is the space of irreducible representations, and here is also a space of irreducible representations, so which for commutative algebra coincide with this set of characters. And so this map maps irreducible representation to the corresponding central character. So centrum always acts by a character on irreducible representation, and we map irreducible representation to central character. And the symmetric sub, so we call this this map also by iota with star, and Y is symmetric if and only if there exists some overlined U is symmetric if and only if there exists U with bar subset C such that U is inverse image of U with head. Yeah, that's easy because it's the only place where this map fails to be bijective is the double points. So actually, this map is the resolution of double points. It just collapses those double points into ordinary classical points. Yeah, and so I think everyone, so it's easy to deduce what we do next. We just take the algebra. So for U, some subset of C, U bar, we take the non-commutative holomorphic functions. I will denote the lower index. I will add the lower index to not confuse between non-commutative functions and commutative functions. On iota -1 of U bar is some symmetric set, and if U is take open U, and if U bar is open, then the inverse image is also open. And we just take it to be this, again, this tensor product. Tensor product of what? Of C d infinity or times over centrum on holomorphic functions on U bar. Yeah, that's how we do it. And there exists a holomorphic functional calculus in this case. So if spectrum is symmetric and U is open, then we have holomorphic functional calculus, and it is easy to construct it. So first, so here the holomorphic functional calculus has this form. So first of all, the element, if the element y again acts by this matrix, and then z, it is like it is easy to prove that the spectrum of, or that z acts like this, y plus plus, and here is minus y minus minus. So the spectrum of z is the spectrum of y plus plus in case of symmetric spectrum, and the same as minus spectrum of y minus minus. Yeah, and so we can so if we have a symmetric open subset, and we just use this tensor product to construct the holomorphic functional calculus in this case. So if U bar is open and it contains the spectrum of Z, then we construct a holomorphic functional calculus. Then this algebra acts on V, on our Banach space V, and how it is easy. So so an element of this algebra is an element of a tensor product. It's so let's call it like, for example, S or times tensored with some holomorphic function f, and we map it to an operator ps, F P Z. P is a VP is a Banach representation again. So we can take homomorphic functions in the neighborhood of spectrum, and it is a neighborhood of spectrum of Z. We can take P of S without any additional conditions because it's just a representation, and so we just have a product of P S with a homomorphic function in the element of centrum, and so that's how we receive a non-commutative algebra of homomorphic functions.
I'm sorry, you had a formula with F plus plus G plus minus. It's the same, right? When you act F to Y and Y plus, all the matrix one that was 2 by 2 matrix was F plus plus G minus.
So
yeah, this one is the same.
So in this case, it's like it's the action of certain element of a group algebra. So if we take this basis, so in my in terms of tensor product, the element. So we can actually write what elements act like this matrix. So we take F plus, we take, I think, A minus 1 tensored with F plus, plus A plus 1 tensored F minus. And here I can confuse signs, but other two basis elements. These two basis elements multiplied, tensored by G plus and G minus. And actually, it's the basis, so every element has such form, in basis. So yeah. So that's the same.
Okay.
It's the same for an arbitrary element. So every element of this algebra, can be described by 4 holomorphic functions, because this algebra is a free model of rank 4 over the algebra of holomorphic functions.
Okay. By the way, do you have any integral form of Cauchy, sort of? I mean, just integral out and you have some kernel with a matrix 2 by 2.
I think it would be interesting, but I haven't thought of it yet.
Okay.
So I was busy with more technical details of it, and haven't yet finished it in the good readable text. So I will thank you for the idea. I will definitely think about it later.
Okay, yes. Yeah, would be nice. Something integral form of Cauchy.
Yeah.
I always see, so it seems it should be something like that.
Yeah, thank you. So by the way, we constructed this presheaf only for symmetric subsets, and for asymmetric or non-symmetric subsets, spectrums, it is a bit more tricky, but I will try to make a sketch of what is done here. So I will make a sketch, not by any general construction, but by an example. but an example of a certain subset, and how to construct an algebra of functions for it. There are actually, so let's again have a picture of complex plane without 2 points -1 and 1, and here we have a pair of double points attached to it. So here are he plus minus, and here we have xi plus minus. So suppose that we have an open set that has only one character from the pair. And generally there are two possible. So there are two possible cases of asymmetry. So it may be like this. It has one double point, or one non-paired double point, or it may be like this. So it has two double points, non-paired. Or it may also be like something this. Yeah, it may contain, so it's different cases, and I unfortunately haven't come up with anything simpler than inspecting every case by hand. But let me show what can happen for one particular case. So let U be some subset such that it has he plus but not he minus, and the other pair of characters for simplicity is not in it. So it's U, and so there exists some U bar subset C in C, such that U equals to, again, iota minus 1 U bar with union with one character, he plus. Yeah, but he minus not in U. He minus not in U, and he plus is in U. So this is a possible case of asymmetry. So take so I define the algebra of homomorphic functions on U just to be an algebra of homomorphic functions on a symmetric subset which we defined earlier. Plus C, plus the algebra of complex numbers. So it's just it's not an integral domain. So the multiplication here is just independent on both summands. So it's just the sum of algebras. Yeah, and that is it's the consequence of those decomposition theorem for a symmetric spectrum. So if we have sigma the infty of some v as a subset of u, then we can decompose v into the sum of v0 with symmetric spectrum plus v he plus. And we know what? We know that we can act on v0 with this part, and we act with a complex number on this part. And that's it. So so by the construction on the previous slide, we have iota minus 1 u acting on v0, yeah, because spectrum of v0 doesn't contain character, so so everything works just fine. And we have c acting by multiplication on the character subspace. Yeah, and why c or not something else? Because it's the only so it's like from some general idea that the holomorphic functions should act like should act by operators from double commutant. So it's here why I choose C here, but it may act by something bigger, maybe, I don't know. But for operate the only double commutant of the infinity in this is just C, but let's just skip it. It's the part for another talk. So is the topic for another talk. So I would just ask you to take it for granted. Yeah, and so we act independently on both parts. So we glue it together to an action of the whole, the infinity on U, on V. Yeah, so that's why it's not that, as I said, it's not maybe not that interesting somehow, but I think it is interesting because it may have some good generalizations to other algebras. And yeah, so it's the case when we have only one non-paired double point, and it may also be the case that we have two double points, then we attach just two copies of C, and we act. So it may be the case where this set has two double points like this. Yeah, and in this case we attach two copies of C, and we also construct the functional calculus in the same way. This summand is the abstraction to this pre-sheaf to be a sheaf. So everything just breaks here for the C, because it is it arises out of nowhere, and but here maybe the good solution for this sheaf to become a sheaf, and the good solution for this is called Grothendieck topology. So I'll just say some general things. And in non-commutative algebraic geometry, constructed by Van Oisten and Verschoren in their book from 1980s, they also considering some Grothendieck topology, and this topology is a subtopology of the constructed topology. So we just kick out some open sets, and we allow and we allow only some good open subsets. So here we may allow for non-symmetric subsets, we can allow such subsets. So we can, if we don't have points here, and suppose that our set have double point, and it's if it has only one double point out of a pair, then this double point should be isolated. So I just speak this very fast because I don't really have time for some precise statements, but we want to allow only those open asymmetric subsets in which this double point is isolated. Yeah, and for this, but not like say, but not like this, like in the. So we don't allow this, and we like this. So yeah, that was really fast, and no one I don't think anyone understood something, but I think here is everything what I wanted to say, actually. So I do really hope that the good readable text will be available in June or July, and I will send it to everyone who is interested.
Okay, thank you very much, Boris. Questions, please. So you said something that similar tricks can be applied to a more general class of algebras, right?
So I think that they may be applied. So so I hope that so what we have here is that all the non-commutativity. So the non-commutativity here is arises like double points, and we can see here that all the non-commutativity is resolved by some easy trick. So I hope that maybe it is also a case in some more general, for example, PID algebras, but I don't know, actually. I haven't really tried to do this because they become more complicated. So what we have here is that we play more, if I can say this, with the space of two-dimensional representations. So the space of the representations of maximal possible dimension. And this space actually is, in case of some good algebras, for example, PID algebras, is the classical manifold, and the representations of lower dimensions are attached to it as such singularities and double points. And I hope, it's my conjecture, that that we always can consider first only this set of representations of maximal dimension, and then add those lower dimensions as some singularities which are described which can be described more easily. But it's like the hand waving and nothing else.
Okay, thank you. More questions, please. Well, if there are no more questions, then we thank Boris again. Thank you. And we meet after the holidays. Most probably, our next speaker will be Boris Bekmagambetov, and he will tell us something about free function theory. And this will be on the 11th of May.